In this video, we demonstrate how a novel plasticity rule can explain the development of sensorimotor intelligence. We use artificial robotic systems simulated in a physically realistic virtual environment as a testbed. The actuators of this humanoid robot are switched off to illustrate the physics. We pull the robot indicated by the red ball. Now the motors are enabled and our novel plasticity rule acts in the robot's artificial brain, represented by a neural network. 4 minutes later, the robot develops a crawling behavior based on its individual history, as one of the many possible behaviors we have observed. The robot has only joint angle sensors, and the artificial brain has no specific task and no information about the robot under control. If two such robots are interacting, complex behaviors emerge, such as this apparent fighting scene here. The robots can grasp each other, indicated by the red hands. Let us now look into the details. The sensor values of the robot are processed by a simple neural network, which generates the motor commands sent to the robot. With the help of an inverse model linking the responses of the external world back to the actions, we obtain the learning signal for each synapse. The new plasticity rule is a variant of Hebbian learning, upgraded with a link to the external world. It is simple, local, and biologically plausible. More details are found in the paper. Now we connect the same control network to a hexapod robot. After a very short time, we observe the emergence of the first locomotion gate, here a synchronous tripod gate. After this perturbation by stumbling with the front leg, the gate spontaneously transitions into a tripod gate. Everything happens online without any training. The synaptic plasticity is fast enough to react to different situations on the fly. When confronted with obstacles, the robot probes different motions, and here transitions into the first gate again. In order to facilitate the development of a certain class of gates, the system can be guided by providing a few symmetry properties of these gates. In this experiment, we attach the hands and feet of the robot to cranks of heavy wheels. The upper and lower body parts are essentially decoupled because the robot sits on the stool. Initially, the wheels get spontaneously spinned by the robot. Due to their inertia, they also exert reactive forces on the robot, which lead after some time to the development of a smooth spinning behavior. We are tempted to say the robot found a task, namely rotating the wheels. Now we apply a torque to the upper wheel to invert its spinning direction. Interestingly, the robot takes up the new direction quickly and maintains it. In the case two robots are interacting in such a scenario, we witness the spontaneous cooperation of both robots. They only communicate by forces applied to the wheel. Again, these robots don't know anything about the partner, the wheel, and their own body. Nevertheless, our plasticity rule leads to such specific behaviors. One of the reasons is that it enhances velocity correlations between the joints, and secondly, that it takes the reactions of the external world into account. More information can be found in the paper.